So I decided to talk about just one particular thread of what I do, which is related to SD shell model interactions. And I decided to also break it up into two parts. I thought I'd give a bit of history, and then my student Aaron will fill you in with the latest details. The history thing sort of came up because I realize I've been doing these sort of things for about 50 years, and the USD is about 50 years, so it's all sort of fits together here. And so let's start just the big picture. We're working in this intermediate scheme of effective theories. And we're working in the nuclear shell model, which is to say that we truncate to the SD shell, and we have to take into account all those things which are not in the model space. And so we have a core, which is red, we have a valence space, and we have an empty space, but actually all those things are involved in the levels that we look at. So we have to think about all that. So the history of this starts around 1968, I think, with two kind of breakthrough ideas. One is Kuo and Brown worked to develop a theory that takes nucleon-nucleon scattering potentials and to develop a G matrix for short-range correlations and to develop core polarization. And then they applied it to two particles in the SD shell and two holes, and it worked rather well. The other thing was that at the same time, for the SD shell at least, Chung and Wildenthal developed many-body techniques to apply those two-body matrix elements, the same ones, to a wider range of nuclei. And they found that the spectra became worse as you had more valence nucleons, particles, or holes, but they could be greatly improved with some small modifications in those two-body matrix elements. So when I first came to MSU as an experimentalist in 1976, Wilton Chung had just finished his PhD thesis on the SD shell. And in the thesis, they were able to look at the lower part of the SD shell and the upper part, and to develop two different Hamiltonians that worked very well on the two ends, but didn't quite fit together. So, and the problem was really, it was a big computational problem. Silicon-28 was very hard to do back in those days, in the middle. But then from 1976 to 1982, computers got better, and a lot more work was done by Wildenthal, and he eventually added a lot more data. You could finally calculate your silicon-28, and you could derive a universal, what's called universal, and that's where the word USD comes from, Hamiltonian for the entire SD shell. The success at that time was related to the introduction of a smooth mass dependence of the two-body matrix elements, but it turns out that this is only part of the reason. The main reason is that it just took more work to develop what the changes were. This was reported as an abstract in the Bulletin of the American Physical Society. There was no coulomb, isospin was conserved, and the RMS deviation in the difference between experimental and theoretical excitation energies was about 180 keV. I'll just use that number from now on as the RMS difference. And in fact, by 1983, Hobson had talked about this and many of the applications in a international school in Sicily. So this is one of the references for the original USD. Now, from 1982 to 88, several things happened. Eric Ormand added coulomb and isospin breaking interactions. And so there's a new class called USDCD for charge dependent, and it's in a proton-neutron basis. And I and others made many applications of the USD interaction and the USDCD. And all this was summarized in a review article, which is also often cited as a reference for USD, which is there. This is sort of a example that was given from the very beginning, a before and after picture. If you just take the Quo Brown for sodium-22, the matchup of the levels looks like that. And if you take USD, it's much better. So that fine-tuning of the matrix elements makes a huge improvement of the details. And odd nuclei are nice examples of details. Also, at the same time, we were asking ourselves, can we take the SD out of USD? In other words, can we make a truly universal interaction that goes beyond the SD shell? And we wrote this paper for Annals of Physics. And we understood several things here. We can make what's called a spin tensor decomposition. We could try to use one boson exchange potentials. And we ended up deriving what's called a best fit interaction based on those ideas, which is a 14 parameter. And the RMS was around 260 keV. But we could not really find a universal interaction that worked for both the SD and the FP at the same time. Even though we had lots of ideas in this paper that were used, we could not find a single interaction. And just to comment, I think one of the issues here, there's three issues. One is the three-body force, which I'll come back to soon. And the other is that what we call core and single particle energies are a combination of kinetic and potential energy contributions. And in these fits, we can't distinguish those two contributions. The wave function only depends on the total. But the interpretation of the TBME in terms of potential does depend on this. So this is something I think that limits how we can interpret what we do here. From 1976 to 82, the problem was the USD was only really never documented. There was no paper that told exactly how it was derived. It was actually quite complicated, many iterations of what's called single value decompositions. So I decided around 2004 that this should be done properly. And so I took another starting point. We always start with the best ab initio interaction, and this is one from Morten Korth-Jensen. And Werner Richter helped to put together a complete set of data, which is shown on the right-hand side. And two new USD interactions were derived with the single value decomposition method, USDA and B. The first one had 30 linear combinations of parameters, and B had 56. And then when we just tacked on Ormand's charge dependent, these made USDA and B, CD. So we were still, at this point here, limited to good isospin. We only put in energies for N equals Z and neutron-rich nuclei, as you see on the right-hand side there. So in 2018, my new student, Aaron, who you'll hear just after this, completely rewrote all the codes for doing single value decomposition, and we moved over to a proton-neutron basis using outputs from nushell X. And he included coulomb and isospin non-conserving interactions explicitly. And these resulted in two new interactions, a USDC and USDCM, which he will explain. And he also used as a starting point in medium renormalization group results for silicon-28, and these are called I and IM. So we're just making the family of USD bigger and bigger, and this is the paper that we published this year on that. And as you see on the right-hand side, this includes explicitly data for both neutron and proton rich, and he will explain all the nice details of that. 2017, we see the start of the development of what are called nucleus-dependent Hamiltonians. And the example in the paper below is with in medium similarity renormalization group method, IMSRG. And several things are going on here. One is that the three-body interaction is finally explicitly included, but not as a three-body in the valence space. In the valence space, as you see from, if you look at the diagrams on the right-hand side, what happens is that you take a certain nucleus in the SD shell, like silicon-28, and then you average the three-body term over the inert core or the other nucleons. And you end up with an effective two-body interaction, which is nucleus dependent. And that's the first paper they did, and the second paper actually shows a little bit more of what the issues are here. So these are non-empirical. Ours are empirical because they're tuned to experiment. These are non-empirical because they're completely non-tuned. They're completely ab initio. And what you see in the bottom is what they put together in terms of the RMS deviation plots. First of all, if you just take the bare two-body, as we sort of did back in 1980, you see the RMS deviation over on the left-hand side is about something like 2 MeV or so. And what we did early, what Wildenthal did, is that he went from this picture to this picture all the way to the right-hand side, in which the RMS was in this picture is 220. It can, if you just look at the levels that are in the SD shell, it's about 180. And with their nucleus dependent IMSRG, what they call valence space IMSRG, this is the deviation. It's not bad. The RMS is down to around 650. So this is where we are now. We made this big loop jump from here to here. Now we're here. And I think the question for the next 10 years or so is going to be, how do we improve this middle panel? How do we go from here to here in some way that we can work with and understand? So yes, that's my introduction. I mean, let me just be sure, that's it. And then I'm going to take off my screen, and Aaron will continue.
Okay. I think you have to stop screen sharing before I can share.
All right. Let's see if I can find that. Okay, and screen share. Did I stop? Oh,
yes.
Apparently.
I think I've got mine up, right?
Good.
Okay. So yes, thank you for the history and introduction, and thank you all for coming to the talk today. As Alex said, I'll be continuing on talking about isospin breaking shell model interactions in the USD shell. Yeah. Can
you do it full screen, or?
Is it not full screen?
Oh, not for me. Oh, not for me. Oh, no, it is. Okay, I'm sorry.
Okay.
Yep, it's done.
So yes, so just to preview the talk today a little bit, we'll be talking about the new isospin breaking USD Hamiltonians, USDC, that were mentioned. Some applications that we use them for, looking at binding and separation energies, talking about Thomas Airman shifts, and looking at some cases of isospin level mixing. And then I'll talk about a little bit about my ongoing thesis work, revisiting the isovector strength in the USDC interactions and an extension into the SDPS shell. So we see, again, we're working in the configuration interaction space, and then this is just a nice picture of the SD shell, showing it from oxygen 16 to calcium 40. So this is that same plot you saw before, showing the distribution of levels that are used now in USDC and USDCM for the fit. Like he said, the biggest change here is that we are now including all of these proton-rich nuclei, and that change comes from the fact that we've switched to a proton-neutron formalism and are going to include the coulomb and isospin breaking interactions directly. And because of this, that means that in the past, the USD interactions had a charge-dependent correction added to the ground state binding energies, and we don't have to do that for this interaction. Additionally, we've added in parameter uncertainty tracking, just using the standard covariance matrix method to extract fitting parameter uncertainties. And then for the fit, what we do is we start with a realistic starting interaction so that we're not wandering randomly through parameter space, and we use USDB as our starting point for our strong interaction. We have an analytical coulomb with short-range correlations for our coulomb interaction. And then as a starting point for our isospin non-conserving interaction, we are going to insert a 2% isotensor strength increase for the proton-neutron T=1 two-body matrix elements compared to the PP-NN two-body matrix elements in H0. And then we are able to do this fit in sort of stages where we fit each individual part on its own. So the first stage is doing the fit has been done in the past using a singular value decomposition fit of the energy levels to constrain the strong interaction while holding the coulomb interaction and isospin non-conserving interactions constant. Then optionally, we have the chance to constrain the coulomb interaction using the B coefficients of the isobaric multiplet mass equation, which are essentially the mirror energy differences weighted with the isospin of the nucleus you're looking at. And then lastly, we have constraint for the isotensor strength using the C coefficients of the IMME, which we'll talk about. So just a quick slide to throw up everyone's memory of what the isobaric multiplet mass equation looks like. It's just a quadratic equation that relates the masses of isobaric multiplet states on a nice little parabola. We can use the liquid drop model to look at what the coefficients of this equation should look like if we're assuming no shell interactions or no shell model. We can see that B sort of grows linearly, roughly, and C drops off as a to the minus 1/3, and they're at two different scales. So we'll be using those. So I just wanted to throw this slide up to make sure we're all on the same page. So the first stage we could do is modify the coulomb interaction, which just how we were able to modify the strong two-body matrix elements to get better reproduction of the energy spectra in nuclei. We can do small changes in the single particle energies and two-body matrix elements of the coulomb interaction to help account for things that might be missed by the model assumptions. So changing RMS charge radius, for example, in your excited states of a nucleus, a small change in that charge radius could result in on the order of 100 keV shift in your energy. And since we're looking at about 150 keV energy RMS, that's something we want to try and account for. So we performed just another singular value decomposition fit on these two-body matrix elements and single particle energies. But instead of just to the energy levels, we fit to the mirror energy differences. And there's about 200 of those in our data set. So looking on the right here, we can see this plot shows the delta mirror energy difference. So that's the difference in mirror energies differences between theory and experiment. So you want to hug zero. You want every point here to be on zero for theory and experiment to match completely. And we see this top here is using this analytic coulomb. And then the bottom here uses the constrained coulomb, where we've constrained to the B coefficients, and you see that we've got this nice tightening up of this spread around zero. And then this plot in the middle shows the small changes that were made to the two-body matrix elements. So there are roughly two main groups of these two-body matrix elements, diagonal and off-diagonal, and with small changes to those, we're able to get much better agreement. So next, we're going to look at tuning the isotensor strength. Again, we're modeling the isotensor strength as a % increase to the T=1 proton and neutron two-body matrix elements compared to the average strength of the PP and NN two-body matrix elements. Literature suggests this is about 2%, that strength difference. So we want to find a way to constrain this given the data set we have. And what we're going to look at first are the C coefficients. And we're going to look at the T=1 C coefficients because they're easiest to visualize. On the left here, we're plotting the experimental T=1 C coefficients across the SD shell in these black points. And then we have this dashed line, which shows the C coefficients if our theory only had coulomb and no isotensor. So you see, if we only include coulomb, we get a very small oscillation, but nowhere near the strength of the experimental oscillation. So we want to, first, let's understand where this oscillation comes from. We can look on the right here and look at these T=1 triplets, and I've split them into two groups here. Whether the triplet in question has a core nucleus that is even, or a core nucleus that is odd. And that is what gives this oscillation, this pairing effect between those two. And so you see when we add in this isotensor effect, about 2% increase, we get a very good agreement with experiment. And that tells us we can use this as a way to tune in exactly what we want that isotensor strength increase to be. So doing so, we end up with 4 new interactions total. The first two were USDC and USDCM. The difference between these two being whether we have the ab initio coulomb in USDC or the modified coulomb in USDCM. In the case of USDC, this fit to the C coefficients produced a 2.2% isotensor strength increase, which is roughly consistent with literature and what we expected of about 2%. And then USDCM, with its modified coulomb, only ends up needing a 0.8% isotensor strength increase. And you see here, this dashed line is now showing USDCM C coefficients versus USDC C coefficients. And you see that USDCM has poorer agreement with experiment compared to USDC. And so there was a trade-off. We got better improvement on our mirror energy differences in B coefficients, but we lost some agreement with the C coefficients. And then, as Alex said, we also developed the USDI and USDIM interactions that were fit with the same data and methods, but based on more modern IMS-RG interactions. And then this plot here is just showing those fit uncertainties versus the absolute difference in the USDC and USDI two-body matrix elements. So you can see that when USDCI and USDI disagree, it's often in off-diagonal matrix elements. And then again, they disagree more when the fit is uncertain about what that value should be. So the larger the uncertainty, the more disagreement you'll have between these two interactions, which makes sense. So the first big improvement that I'll point out with USDC over the old interactions USDBCD are an improvement in the nuclear binding energies across the shell. You see that with USDBCD, we get this fall off as you get to the top of the shell, and this causes problems with calculating separation energies at the top of the shell. But we solved that problem here, and we've maintained good agreement with the excited states and the ground states, except for these notable nuclei that stand out, which we will talk about right now. So the disagreement with the experimental binding energy in the SD shell comes primarily from the island of inversion, which is a region of the nuclear chart around the n=20 shell closure, neutron shell closure, where the ground states in experiment are actually about 2 MeV below what the shell model predicts. And this comes from the fact that 2 neutrons sitting in this SD orbits, due to a level inversion, will promote and sit in FP orbits, creating another 0+ state below the predicted 0+ state for the ground state. And dealing with this would require an explicit extension to a full SDPF neutron orbit, which makes the problem very difficult dimensionally and very complicated to solve. But it does motivate our limited extension to the SDPF restricted shell, so we can examine the other side of this island inversion and map out it completely. Looking now at the proton drip line, so the other side of the shell, we are going to look at 2 nuclei. The first is argon-31. A couple years ago, there was an experiment to measure the 2 proton separation energy of argon-31, and they were able to extract a value that is consistent with 0, but our new interactions agree fairly well with this recent experiment, with a great improvement compared to USDB-CD with agreement. And then additionally, we have a unique case in the SD shell, calcium-34, which is bound to proton emission, but unbound to 2 proton emission. This was, we helped calculate or predict some separation energies for NSCL proposal on neutron deficient calcium isotopes, and that experiment was accepted and ran just this past October. Was one of the last experiments at the coupled cyclotron facility, so that's exciting, and hopefully we get something interesting out of that to compare to our results. I would like to talk now about a treatment that we came up with for Thomas Airman shifts, which are something that the USD interactions can't fully calculate. So the Thomas Airman shift is experienced by a S1/2 proton that is near the proton separation energy threshold. Due to its S1/2 nature, it has no angular momentum, so it can spread out radially, and this causes a decrease in the Coulomb repulsion and a positive shift in the binding energy. And we can model this using a skirm interaction to vary the depth of the well that the proton sits in to come up with a relationship between the Thomas Airman shift it experiences and its proton separation energy. And using this single particle separation energy combined with spectroscopic factors, we can predict the Thomas Airman shift for many states, or any state in the SD shell, really. And we can look at some selected states here that have no large Thomas Airman shifts. And you see that without this skirm interaction correction, USDC and USDCM are not able to predict these larger Thomas Airman shifts. Another thing we can do with these interactions is look at isospin level mixing and extract isospin level mixing matrix elements to compare to experimentally measured ones. 2 such cases of that would be in sulfur-31 and sulfur-32, which ran at the NSCL and the Texas A&M cyclotron. We can see here in this table that the experimental values are about 41 and 27 keV, which are in pretty good agreement with USDC. USDCM predicts a little bit stronger mixing, but USDB-CD predicts a lower mixing than what we get with our new interactions and from experiment. Another case of isospin level mixing that we've worked on is the A=32, T=2 multiplet. Actually, we finished a paper with this group on the detailed study of the decay of argon-32, but that was focused mainly just on chlorine-32's states. Triambic's group is working on a larger examination of the entire isospin multiplet. And this isospin multiplet requires experimentally large cubic correction of the IMME, so a D coefficient is needed to add to recreate experiment, and it's very statistically non-zero. USDC and USDI are actually able to predict a very similar D coefficient, and the calculations predict that it's primarily due to significant isospin level mixing between the T equal 1, between the T equal 2 0 plus isobaric analog state and nearby, possibly observed in chlorine-32, T equal 1 0 plus state. And on the left here, we're just seeing the prediction of the isospin mixing matrix elements for the 3 nuclei that are involved in this multiplet, so chlorine-32, sulfur-32, phosphorus-32. And we see that all 4 of the new interactions predict rather large mixing across this collection of nuclei, especially compared to USDCD. So we're working on extracting a value for that and comparing, so look forward to that paper coming out. I think the last thing I'm going to talk about now is revisiting the Isovector interaction. So we have an isotensor strength interaction in our USDC, but we don't have an Isovector, and that was because there wasn't a sufficient constraining data set. But we want to revisit that now. So we're going to model this as the relative strength of the proton-proton interaction over the neutron-neutron interaction, which is difficult to measure experimentally because you need neutron-neutron scattering, which is difficult. So first, I want to recall the 2 types of triplets we examined, where we have this odd-even staggering that causes this oscillation in the C coefficients. Let's now look at the B coefficients a little bit more closely. So I plotted here the B coefficients across the same region of the shell. You see that they grow from 3.5 to 7. And we're now looking at the T equal 1/2 doublets. So these nuclei sitting on either side of the N equals Z line. And we're going to now look at a sort of a difference of the B coefficient. So we're going to look at B of A minus B of A minus 2. Because if you look in this plot, you can see this small oscillation of growth, but it's much more apparent when you do this difference. So we can see this strong oscillation of the difference of B coefficients as you go up the shell. It goes right around the liquid drop model's expectation of what this difference should be. But we see an inverse now. We see that USDCM is better at predicting this oscillation as compared to USDC, which is not able to always give this oscillation. And we can view this in a similar way where we group our doublets into 2 groups, particle plus an even-even core or a hole plus an even-even core. And you can see that here where this oxygen-17 and fluorine-17 doublet can be modeled as either a proton or a neutron sitting on top of an N equals Z nucleus. And then this other doublet can be modeled as a hole in an N equals Z nucleus. So we believe that adding in an isovector strength to USDC would allow us to reproduce this oscillation and thereby increase our agreement with the B coefficients without sacrificing our agreement with the C coefficients that we saw when we modified the coulomb. So to conclude, we have these developed 4 new USD type Hamiltonians that are explicitly isospin non-conserving. We have USDC, which is based on the same renormalized G matrix interaction that USDA and B were. We have USDI, which is based on more modern IMSRD interactions, and we have the modified coulomb versions of each of those. We looked at some interactions. We looked at the interactions predictions for properties of nuclei across the SD shell, looking at binding and separation energy improvement, treatment for Thomas-Ehrman shifts, and isospin level mixing. And for ongoing thesis work, we're still continuing to work on adding the isovector strength to the SD shell to improve those B coefficients without modifying the coulomb and maintain our good C coefficients. And we want to extend this to the SDPF space to better understand the island inversion. So that is all I have. So thank you.
Thank you very much, Aaron and Alex, for a wonderful presentation. So there is a hand by York. Can you unmute your mic and ask the question or comment?
Yes, yes. So Aaron, that was very, very nice presentation.
Thank you.
I'm very, very glad that you're doing so well, working at MSU with Alex. So my question is, have you looked at the Nolan-Schiffer anomaly or any other place that Coulomb interaction is not sufficient and you really need these isospin violating interactions?
I'm afraid I'm not familiar with the Nolan-Schiffer interaction, okay. So I haven't quite looked at that now.
Alex, can you comment?
Yeah, let me answer. We are using, of course, experimental single particle energies for the fit. Nolan-Schiffer is a matter of interpreting those energies in terms of Coulomb, potential, and all that. And so that's something that is beyond what he's doing.
Okay, but I mean, is there any clear signature for the need of isospin violation beyond Coulomb that you have seen so far?
Well, I mean, as far as reproducing the C coefficients, which are here. We are unable to produce the experimental C coefficients without an isotensor interaction added on top of the coulomb. So I would say that that's evidence that we would need the isotensor interaction.
Thank you so much.
Yep. Thank you.
Thank you. Are there any other comments, questions to Alex and Aaron?
Hi.
Yeah.
I had I was very interested in the remarks about the early shell model, because we were doing these measurements on sodium-22. Can you hear me? I take it you can.
Yes, we can hear you.
And we had calculations done by Duncan MacArthur from Canada, who wrote up the sodium-22, which is the odd-odd nucleus. And you can see there all the differences in the various so-called rotational bands predicted by the shell model, and how for each band the strength was distributed differently throughout the SD shell. And if I can produce it, I have a slide of that. But what can I do? Share the screen.
Let me stop sharing mine then. There you are.
Sorry about that.
No, you're good.
Let's have another go. This one. Can you see this?
Yes.
I have a thing saying uses Glasgow basis code, Rex Whitehead and Sandy Watt. But hang on a moment. Damn things. Right, there. Come up here. Does that work? Anyway, but it was very interesting, but it was buried in the Canadian Journal of Physics, volume 54, if you want to look it up. Duncan MacArthur, J.D. MacArthur, and it was very, very useful. It used Hobson-Wildenthal's interaction, and but with the Glasgow M-basis code written by Rex Whitehead and Sandy Watt and co. So it was very impressive and very useful to us. We could do all the measurements of the spins and parities for the first time, because Peter Twin at Liverpool discovered how to use the polarization to give you unique spin values. So that was very valuable. Okay.
Okay, thanks, John. That was, of course, I only really talked about just a few of the papers that were involved in the derivation.
Yeah. Sure.
There were hundreds of other papers that were influential back starting in the 50s and 60s. And in fact, the collective models were really the first ones to be used. But eventually, the shell model just replaced the collective model because it was much more predictive. With the collective model, you always had to argue what the shape was, what the beta was, and so forth. But in the shell model, it all just came out. But I should say that the early history is dominated by the collective models in the SD shell.
Yes, Zach. He said he has some comment.
Yes. Hi, Alex. Thank you very much. Very nice talk. I would like to make a comment on the DFT treatment of these isobaric mass equation coefficients. If I may share my screen with you. Try to do that. Okay, so this is the DFT result of all this physics, where we can reproduce the staggering of triplet different equation and mirror difference energies with 6 parameters across the entire mass region where they have been measured, including a very interesting effect of staggering of MGE, which appears and disappears in different regions of nuclei. So I will share with you the reference to this paper. This could be an interesting contribution to our today's discussion. Thank you very much.
Yeah, thanks. I know that work. So that this issue of the staggering of the B coefficients is, to me, a relatively, new thing, and there's a lot of detail in there, coming essentially from for us, it's coming from the pairing part of the Coulomb force. Yeah, but thanks.
Okay, thank you, Alex. Nico, you can take over for the student awards.
Okay, thank you very much, Tiff and Nikita, for sharing the session and for